Hello friends, I welcome you in lecture number 3 on Laurent series. In this lecture we are going to discuss another interesting example for Laurent series expansion of a given function. So let's start with this example. We are asked to expand this function 1 divided by z times z square minus 3z plus 2 in different regions. First region is 0 less than absolute value of z is less than 1. Second is absolute value of z in between 1 and 2, and absolute value of z is greater than 2. So first we discuss why we are given these three different regions. And so as we know, our function must be analytic in the annular domain if we want to represent it in terms of Laurent series. So if we factorize this quadratic factor, we will obtain z minus 1 into z minus 2. So this function f of z is a rational function in which denominator is z into z minus 1 into z minus 2. So as we know, rational function is not analytic at those points at which denominator becomes 0. So here denominator becomes 0 at these 3 points 0, 1 and 2. So this function fails to be analytic at these 3 points 0, 1 and 2, and it is analytic everywhere except these 3 points. So and we are asked to find out expansion in these domains. So if we write z in this form, then here we are asked to find out Laurent series with center 0. That means we are interested in the Laurent series in powers of z. So here center of the Laurent series is 0. So we have to think for this type of domains r1 less than z minus center less than r2. So if we compare given domains or given regions, we can see that center of required Laurent series is 0. So we require annular domains of this type r1 less than absolute value of z less than absolute value less than r2. Now function is not analytic at these 3 points. So suppose we consider this is a complex plane. Now function is not analytic at z equal to 0. Suppose this is z equal to 0, suppose this is 1 and this is 2. So function is not analytic at these 3 points 0, 1 and 2, and center of the Laurent series is 0. So we are interested in this type of annular domains in which function is analytic. So if we consider circle with center 0 and radius 1, then suppose this is circle with center 0 and radius 1, then in this circle function is not analytic at z equal to 0, which is inside the circle, and function is not analytic at z equal to 1, which is on the boundary of the circle. So if we exclude the boundary and if we exclude the center z equal to 0, then we have this region 0 less than absolute value of z less than 1. Now function is not analytic at z equal to 2 also. So suppose we consider circle with center z equal to 0 and say radius 2. Suppose this is the circle with center z equal to 0 and radius 2, then function is not analytic at z equal to 2, function is not analytic at z equal to 1, function is not analytic at z equal to 0. So I have to exclude these 3 points. So if I consider this region between two circles of radius 1 and radius 2, that is, if I consider all the points which are outside the circle mod z equal to 1, then I have to consider absolute value of z greater than 1, and if I consider all the points inside the circle mod z equal to 2, then I have to consider mod z strictly less than 2. So this region is nothing but a region between these two circles. Region between the circles mod z equal to 1 and mod z equal to 2. So this is nothing but a region given by 1 less than absolute value of z less than 2. This inside region is nothing but region given by 0 less than absolute value of z less than 1. And if we consider a region outside this circle mod z equal to 2, then this region is unbounded. Function is analytic at all the points outside this circle mod z equal to 2. So this region is unbounded. So here absolute value of z is greater than 2 and there is no upper bound, so that is another domain 2 less than mod z less than infinity. So because our function is not analytic at z equal to 0, 1 and 2, we are having 3 different annular domains in which function is analytic. This domain 0 less than absolute value of z less than 1, then a region between two circles 1 less than absolute value of z less than 2, and region outside the circle mod z equal to 2, which is given by 2 less than mod z less than infinity. So our function is analytic in these 3 different annular domains, and we are asked to expand our function in all these 3 domains, and we have to consider center of the series as z equal to 0. So all these annular domains are centered at z equal to 0. So we expand our function in different domains one by one. First we simplify our function. Our function is f of z is 1 over z into z square minus 3z plus 2, and this quadratic factor is nothing but product of two linear factors z minus 1 and z minus 2. So this is proper rational function. So first I represent it as a sum of partial fractions. So this we can write as a divided by z plus b divided by z minus 1 plus c divided by z minus 2. First we represent our proper rational function as a sum of partial fractions. So if I multiply whole equation by z minus 1 into z minus 2, I obtain a times z minus 1 into z minus 2 plus b times z into z minus 1 plus c times, here I have to consider z minus 2, and here z times z minus 1. Here z is present, so here z is absent. Here z minus 1 is present, so here z minus 1 is absent. And here z minus 2 is present, so here z minus 2 is absent. So now first we put z equal to 0 in 1. So we have left hand side is 1. This is a times 0 minus 1, 0 minus 2. So this implies 1 equal to 2 times a. So we obtain a equal to 1 by 2. Second linear factor is z minus 1. So we put z equal to 1 in given equation. Left hand side is constant 1. And this will become 0 for z equal to 1. And here we obtain b into 1 minus 2, that is minus 1. This gives me b equal to minus 1. And finally we consider z equal to 2 corresponding to linear factor z minus 2. So we have 1 equal to, for z equal to 2 we have these two terms 0 and this is 2 into 1. So we obtain c equal to 1 by 2. So we put values of ABC in this expression and we see what we obtain. So therefore f of z is a divided by z, that is 1 by 2 into 1 by z, b divided by z minus 1, b is minus 1, so we have minus 1 over z minus 1, plus c divided by z minus 2, c is 1 by 2. So this is a representation of given function as a sum of partial fractions. So now we consider the expansion of function in different domains. So first we consider the domain, say 0 less than absolute value of z less than 1, and we will keep in mind that we are not going to use Lorentz theorem. We are going to consider that standard Maclaurin series expansion of this function, which is 1 plus z square and so on. So we will try to represent all these partial fractions in this form such that absolute value of z is less than 1. Okay, fine. So now here this in the first term, this is already in powers of z, so we keep it as it is. This we have to express in this form, so that we will write as minus of 1 minus z, and because absolute value of z is less than 1, we will use this one. Here we will represent in this form 1 over 1 minus something, so in that we will take minus 2 common, and we will have 1 minus z by 2, and because absolute value of z is less than 1, absolute value of z by 2 is also less than 1, so we can use that formula here, this formula. So first we rewrite our function in this form 1 over 1 minus something, and then we see what we obtain as a expansion of given function. So first we write our function f of z is 1 over 2z. This I rewrite as, I take negative sign outside, or we first write our function here, and this is 1 by 2 times 1 over z minus 2. So we keep this as it is. Here we take negative sign outside, so we have 1 over 1 minus z, and this we can rewrite as, if we take minus 2 common, this we can rewrite as 1 minus z by 2. We can check by multiplying also. This is minus 2 into 1, minus 2, and minus 2 into minus z by 2, that is this. Now in our region, absolute value of z is less than 1. So first we write one more step, we keep this as it is. This we can rewrite as minus 1 by 4, 1 divided by 1 minus z by 2. Now absolute value of z is less than 1, so therefore absolute value of z by 2 is also less than 1, because absolute value of z by 2 is less than absolute value of z, and this is less than 1. So now we are able to use that Maclaurin series expansion. So this we keep as it is. Here we write, this is 1 plus z square plus z cube and so on, and in this series here instead of z we have z by 2, so we will write 1 plus z by 2 plus square of z by 2 plus cube of z by 2 and so on. And this is possible because our region is 0 less than absolute value of z is less than 1, therefore absolute value of z is less than 1 and absolute value of z by 2 is also less than 1. Now we consider common powers of z, and common powers of z we collect here we have 1 by 2z, and if we consider constant terms, then here 1 is constant term, and if we multiply this minus 1 by 4 with this, another constant term is minus 1 by 4. So we consider 1 minus 1 by 4. Similarly, we collect power of z. Here power of z has coefficient 1, so it is 1, and if we consider this z by 2, so coefficient of z is minus 1 by 8, that is 1 minus 1 by 8 times z. Similarly, coefficients of z square, here it is 1, here we will have 1 by 4 and into minus 1 by 4, so coefficient will be minus 1 by 16, and so on. We can write one more coefficient for z cube. Here we have 1, and here this is 8 into minus 1 by 4, so that is going to be 1 minus 8 into 4, that is 32 times z cube, and so on. And this is valid for 0 less than absolute value of z less than 1. So now we rewrite all these terms. This is going to be 4 minus 1, that is 3 by 4. This is going to be 7z by 8. This is going to be 16 minus 1, 15z square by 16, and 32 minus 30, 32 minus 1, 31 z cube, and so on. So, and this is nothing but our function f of z. So we can see we have obtained this expansion in powers of z. There is only one term in which we have negative power of z, and this expansion is valid in the domain 0 less than absolute value of z less than 1. Now we consider second domain. Second region is z lies in between circles mod z equal to 1 and mod z equal to 2. So we have 1 less than absolute value of z less than 2. So first we write our function. It is 1 over 2z minus, let me check it, minus 1 by z minus 1 plus 1 by 2 into z minus 2. Let me check again. 1 by 2z minus 1 by z minus 1, 1 by 2 into z minus 2. So now here we have absolute value of z is greater than 1. So that means 1 is less than absolute value of z, or 1 by z has absolute value less than 1. So we have to be careful. We cannot use this series here, 1 over 1 minus z equal to 1 plus z square, and so on, because for this series we require absolute value of z less than 1. So this we cannot use in this region, because absolute value of z is bigger than 1. So for that we rewrite our function. This we rewrite as we consider z common here. So if we take z common, we will have z times 1 minus 1 by z, and absolute value of 1 by z is less than 1. So we will use that Maclaurin series expansion. In place of z we will put 1 by z. Now here same thing here, here absolute value of z is less than 2. So if we consider these two on left hand side, absolute value of z by 2 will be less than 1. So here we can use, first we consider this minus 2 common. Suppose we write this as minus 2, then this is going to be 1 minus z by 2. minus 2 plus z. So we will write z minus 2 as minus 2 times 1 minus z by 2, and absolute value of z by 2 is less than 1, so that will work here. So this we rewrite as, we write one more step. Here we take minus 2 common, and here we have 1 minus z by 2. So now we rewrite all these things in proper way. This is 1 by 2z, this we write as, this is as it is, 1 minus 1 by z, and here we obtain coefficient as minus 1 by 4 and 1 minus z by 2. So here absolute value of 1 by z is less than 1, here absolute value of z by 2 is less than 1. So now we are able to use that standard Maclaurin series expansion. So here we have minus 1 by z, and here we have to write powers of 1 by z. So instead of z we have 1 by z, so 1 plus 1 by z plus 1 by z square plus 1 by z cube, and so on. And same thing here, minus 1 by 4, instead of z we have z by 2, so we write 1 plus z by 2 plus z by 2 square plus z by 2 cube, and so on. And here we are using that 1 less than mod z less than 2. This implies absolute value of 1 by z is less than 1 and absolute value of z by 2 is less than 1. So we are able to use that Maclaurin series expansion of 1 over 1 minus z. Here in the first series we are having 1 by z in place of z. In the second series we are having z by 2 in place of z. Now we simplify, we collect the common coefficients. So first we write this as minus 1 by 2z, and here we can write one more step, minus 1 by z minus 1 by z square minus 1 by z cube. We are multiplying with 1 by z, so this is 1 by z, here 1 by z whole square, this is 1 by z square into minus 1 by z, that is minus 1 by z cube. Here we will have minus 1 by z raised to 4, and so on. And if we consider this part, then we have minus 1 by 4 minus 1 by 8 into z minus 1 by 16 into z square. Okay, we have 2 here, so 2 into 4 8, there will be 4 here, 4 into 4 16, there will be 8 here, so 8 into 4 minus 1 by 32 z cube, and so on. And this is valid in the region 1 less than mod z less than 2. So this is Laurent series expansion of f of z in this region. If we wish, we can rewrite in this way. First we consider this series with positive powers of z. So it is minus z square by 16 minus z cube by 32, and so on. This series contains the non-negative powers of z, and plus we can write this 1 by 2z minus 1 by z minus 1 by z square minus 1 by z cube, and so on. So this is the Laurent series expansion in the domain 1 less than mod z less than 2. So this Laurent series has infinite number of negative powers of z also, and positive powers of z are also infinite. Now we consider the last domain. Third domain is we have to find out expansion of f of z in the domain 2 less than mod z less than infinite. So here we have absolute value of z greater than 2. So from this we will have absolute value of 2 by z less than 1. And if absolute value of z is greater than 2, absolute value of z is greater than 1 also. So we will have absolute value of 1 by z is also less than 1. So now we see what is our function and how we can write it appropriately so that we can use the standard Maclaurin series expansion. Our given function is 1 by 2z minus, let me check again, it is 1 by 2z minus 1 by z minus 1 and 1 by 2 into z minus 2 minus 1 by z minus 1 plus 1 by 2 into z minus 2. So this first term we have to keep as it is. Now as we discuss, we have to write our these two fractions in terms of 1 by z and 2 by z. So here if we take z common, then this is z times 1 minus 1 by z, and here also if we take z common, we have 1 minus 2 by z. Because absolute value of z is greater than 2, this implies absolute value of 2 by z is less than 1, and absolute value of z is greater than 2 implies absolute value of z is greater than 1 also. So that implies absolute value of 1 by z is also less than 1. So that is the reason why we are writing this in this form, 1 minus 1 by z and 1 minus 2 by z. We can check here this, if we multiply with z we have z minus 1, and if we multiply with z we have z minus 2. So this is fine. Now we write down this standard Maclaurin series. We replace z by 1 by z. So we will have 1 plus 1 by z plus 1 by z whole square plus 1 by z whole cube and so on. And here in this second part we have to replace z by 2 by z. So 1 plus 2 by z we are writing for this, plus 2 by z square plus 2 by z whole cube and so on. And this is valid in the domain or region 2 less than mod z less than infinity. So now we simplify this. If we observe here, we have 1 by 2z here, and here we have 1 by 2z. So that is going to be 1 by z, and that 1 by z will cancel out this minus 1 by z. So before that we can write by simplifying these brackets. Here we have minus 1 by z into 1 minus 1 by z into 1 by z, that is minus 1 by z square, and here we can see powers are increasing, so we have minus 1 by z cube and minus 1 by z raised to 4 and so on. And here if we consider, we write one more step. This is going to be 1 plus 2 by z plus say 2 square by z square plus cube of 2 divided by cube of z and so on. Okay, so now we further simplify this. First we keep all these things as it is, 1 by 2z minus 1 by z minus 1 by z square minus 1 by z cube minus 1 over z raised to 4 and so on. And if we multiply this bracket by 1 by 2z, we have 1 by 2z plus 1 by 2z into 2 by z, that is 1 by z square, plus here 1 2 will cancel out and we have 2 divided by z3, plus here 1 2 will cancel out, so we have 2 square divided by z raised to 4 and so on. So now we can see this 1 by 2z plus 1 by 2z, that is 1 by z, and that will cancel out this. Also 1 by z square will cancel out, and here we have 2 minus 1 into 1 by z cube if we combine these two. Similarly here we have 2 square minus 1 into 1 over z raised to 4 and so on, and this is valid in the region 2 less than absolute value of z less than infinity. So if we would have written more terms here, then the next term was 2 raised to 3 minus 1 into 1 over z raised to 5. We are getting some pattern here. Here we have 2 minus 1 into 1 over z cube, that is 2 raised to 1 minus 1 times 1 over z cube. Here 2 raised to 2 minus 1 times 1 over z raised to 4. So next term we can imagine, which is 2 raised to 3 minus 1 over 1 raised to z by 5. So in this way we have obtained expansion of f of z in this third domain also. So in this way same function can have different Laurent series expansion in different domains with the same center. Here we have expanded our function f of z in these three domains: 0 less than mod z less than 1, 1 less than mod z less than 2, and 2 less than mod z less than infinity. And in all these expansions we are just using this expansion, and we are converting our functions in such a way that we have absolute value of this quantity is less than 1. So in this type of problems, try to write your function in this form: 1 over 1 minus something. Now whatever you obtain here, absolute value of that quantity must be less than 1, so that we can use this standard Maclaurin series expansion. So this is all about today's lecture. I hope you like this lecture. Thank you very much.